This is Chapter 5. We're learning about integrals, the area under the curve. What we're going to do in this section is approximate the area under the curve. Then in the next section, we're going to learn how to find the precise area under the curve. Let's look at the question that we're really asking and trying to answer because it's different from the one that we've worked on for the rest of Calc 1. You might remember at the beginning of the course I said, well, if we're given a curve y equals f of x, what's the instantaneous velocity of the object in question with this position function at the point x equals a, right? And it turns out that it was given by f prime of a, right, which is the slope of the tangent line. We learned all about how to do that, right? How to find that. That was the derivative of the function, right? So we're going to ask the opposite question in a sense. We're going to study the integral so we can answer the question, what's the net area between a curve and the x-axis on the interval from a to b? Well, let's look at this, right? So if we have a curve on, I don't know, some interval a to b, right? And maybe it goes like this or something like this, right? This is y equals f of x. If we label this guy a1, this guy is a2, and this guy is a3. Actually, let me label a2 in brown. You'll see why in a sec. We would say that the area under the curve on a to b equals a1. Let me use the right one. A1 minus a2 plus a3, right? So we have this notion of positive and negative area, right? Where the area, when the curve dips below the x-axis, we want to consider the area between the curve and the x-axis to be negative. But when it's above the x-axis, we want that to be positive. And it turns out, to answer this question, we're going to define the Riemann sum as the limit. Now, do not worry about this. This is not what we're worrying about in this lecture. I just want to show you where we're working toward, right? It's the integral from a to b of f of x dx, and this assumes that we're talking about the Riemann sum on the closed interval from a to b. I should add, right? This is new notation. Don't worry about it yet. But what this equals is really, it's an infinite limit of a sum from I equals 1 to n of f of a plus I delta x times delta x. And really what this is this is the limit as n approaches infinity of the sum from 1 to n of f of a plus I times the quantity b minus a over n, where n is the number of rectangles, times b minus a over n, right? Where delta x equals b minus a over n, and actually let me just say here, n equals number of rectangles. Now again, you probably should be feeling a little intimidated, but don't be. We're not worrying about this right now. I'm just showing you this is the end game, right? We're going to approximate this. Where do we come up with that formula? Well, the idea is that there is no nice formula to finding the area under just some random curve. So what we do is we approximate it by finding the areas under a bunch of thin little rectangles underneath the curve. So we're going to consider n rectangles, right, where I'm specifying the number of rectangles, each with the same width, which is going to be delta x equals b minus a over n, where again, n equals the number of rectangles. Okay? And so first, what we're going to use is something called left endpoint rectangles, where the height of each rectangle is determined by where the left side of each rectangle touches y equals f of x. So, for example, suppose we have the curve y equals x squared, and we want to approximate the area underneath that curve from x equals 0 to x equals 2. And I say use two rectangles. Okay, Well, and they're left endpoint rectangles. Okay, well, rectangle width equals delta x. That is 2 minus 0 over 2, right? Because we have n equals 2, right? So that's going to equal 1. So let's draw a picture of what's going on, and then let's do the arithmetic. Right, well, we've got the x and the y axes. We've got our curve. We know that, let's say this is 1 and 2, right? We're using 2 rectangles, right? So we know that they're going to be at 0, 1, and 2, right? Those are going to be our interesting values, right? Now, if we're using left endpoints, that first left-hand endpoint rectangle is not going to be very interesting. In fact, it's not going to be a rectangle. It starts at f of 0, right? Because 0 is the leftmost point of our interval. So it starts there and just goes across. Now, for the next rectangle, right, our second one, well, that's going to start at the left of our interval, right? And we go up and up and up. Oh, we hit f of 1. So that's the height of this second rectangle. And then we just go across. And that is our approximate, that's our rectangle approximation, right? And so what we're going to do is we're going to find the area under these rectangles, and that's an approximation of the area under this curve. Of course, it's an underestimate in this case, right? But that's okay. We're just looking for an estimate, right? So we'll say that the area under this curve on the interval from 0 to 2 approximately equals, so what are we really doing? Well, we're finding f of 0 times delta x, right? F of 0 is the height of this first rectangle, right? And then delta x is the width of this rectangle, plus f of 1 times delta x. Again, height times width. We already know this. That's the area of a rectangle, right? So we're just finding the area of rectangles like we learned how to do in elementary school. Okay? So anyway, when we do this out, we know that f of 0 equals 0 squared. We already saw that delta x equaled 1. F of 1 is going to equal 1 squared, and again, delta x equals 1. So this winds up being 0 plus 1, which equals 1. So the area under this curve from 0 to 2 is approximately 1. But we know that that's not the best approximation, right? We're not getting all of this area, right? So let's try using 4 rectangles. And let's see how that does, right? Well, let's see. Again, we take a look at our rectangle width. This time it's going to be 2 minus 0 over 4, which I guess equals 1/2. So a little bit finer, right? Thinner rectangles. Okay, well, I'll try to draw the same sort of curve, just a little more detailed area here, right? We're going to have, this is 2, 1, and I guess we also, let me try that a little bit better. There is, I guess that's 3/2, and I guess this is 1/2. Okay, and again, we're using left-hand endpoint rectangles, right? I guess we also have 0 right here, right? Okay, so again, that first rectangle, not going to be very interesting. It just goes like that. But then the second rectangle, well, we start at 1/2 and we go up till we hit the curve, and then we go across. And then the third rectangle, we start at 1 and we go up till we hit the curve, and then let's try that one again. Go up till we hit the curve, and oh my goodness gracious. Up till we hit the curve. Go across. And then the last one, up till we hit the curve, and then go across, okay? So again, an approximation, right? But it's a little bit of a closer approximation, right? Just visually, right? We're missing some area for sure. It's still an underestimate, but it's not as bad as it was before, okay? All right, you see how, like, this area is a little bit closer to the true area under the curve, okay? So let's take a look at what's going on here, right? We're going to do the same sort of thing we did before, right? F of 0 delta x plus f of 1/2 delta x, right? We didn't just jump to f of 1, right? Because we have more rectangles, right? Plus f of 1 delta x, delta x plus f of 3/2 delta x, okay? And when we do this out, this is going to give us 0 times 1/2 plus 1/2, or I should say 0 squared plus 1/2, right? 1/2 squared times 1/2 plus, what do we have? 1 squared times 1/2 plus, what's that last guy going to be? 3/2 squared times 1/2. We do this out, we get 0 plus 1, I guess that's 1/8, plus 1/2, plus, was that 9/8, I think? And I'm getting 10/8, plus 4/8, 14/8, I think 7/4. I think that's correct. 7/4. So the area under the curve approximately equals 7/4. Okay. Now, just to point out, we also could use right endpoint rectangles, right? Which is the same exact thing, except we're using the right endpoints. So, yeah, that's okay. I'll redraw the thing, right? Same curve. Let's see what we're doing here, right? Rectangle width is going to be the same thing as before, right? If we're using two rectangles, because that just depends on the number of rectangles, not on the endpoints. Same curve. Right? We've got this. Except at this point, we're going to be using the rightmost point of our interval to determine the height of our rectangle, right? So from the interval from 0 to 1, we just go across, and we start at 1, right? We look at 1, we go up and up and up until we hit the curve. That's the height of our rectangle. We do the same thing at 2, right? From the interval from 1 to 2, we go up and up and up. Up, that's where it hits the curve. Well, I guess I need to draw that curve a little bit higher. Right? And up, that's where it hits the curve. Go across. Try that one again. Go across. And that's our height for the second rectangle. There we go. And so now we're approximating the area under the curve by finding the area under these rectangles. Now in this case, you can see that it's a bit of an overestimate, right? But let's see what it is. We're going to get area is approximately equal to, so this time it's going to be f of 1 delta x plus f of 2 delta x, right? And that's going to equal 1 squared times 1 plus 2 squared times 1, which equals 1 plus 4, which is 5. Now remember, our previous estimate had been 1. Here we're getting 5, so there's quite a bit of a difference between these two estimates. Okay? But we also remember that 2 rectangles is not a very good estimate, right? We should have more, like 4, right? So if we draw this curve again, and we have, let's see, if this is x equals 2 and 1, 3/2, 1/2, and that's 0. If we use right endpoints, you see that we're using these rectangles. Whoop. These rectangles, right? These. All right? Same concept as left-hand endpoints, but we're just using right-hand endpoints. Okay? So let's see what we've got here, right? The area, in this case, equals f of 1/2 delta x plus f of 1 delta x plus f of 3/2 delta x plus f of 2 delta x. Right? You see how we're ignoring the 0, but we're including the 2. Every other term is actually the same, right? So let's see, we're going to get, I forgot to mention, delta x does equal 2 minus 0 over 4, which is 1/2 as before, right? So we're getting 1/2 quantity squared times 1/2 plus 1 squared times 1/2 plus 3/2 squared times 1/2 plus 2 squared times 1/2. And let's see what this gets us. So this gets us 1/8 plus 1/2 plus, what was that, 9/8 plus 2. So it equals 10/8, 14/8, 30/8, right? Because it's 16/8, 30/8, which is 15/4, I believe. 15/4, right? Compared to our old answer of 7/4. And that's a pretty big gap, but again, you know, we knew this was an overestimate, so maybe that's not shocking. So the answer lies somewhere in between. Okay? So here's the question. What value does our answer approach from both sides? I don't think that's at all obvious, but it turns out the answer is 8/3. That's the area. How did I know that so quickly? Who knows? And the question is, how do we know that? Well, it turns out the answer is to use infinitely many rectangles, right? And it doesn't matter whether you use left or right-hand endpoints because they're infinitely thin. It doesn't really matter. So you take a limit. We will not be doing that right now. That'll be in section 5.2. Let's do one more example, though. Maybe a messier example for approximation, just for right now, okay? Let's approximate the area under the curve, this guy, from 1 to 11 using 5 rectangles. Let's use left-hand endpoint approximation. I'm not going to draw it. We're just gonna do it, okay? And you'll also note I'm not going to simplify, right? We're working concepts here. One thing also to note is that, notice how we had a delta x on each of those terms right there? I guess I could have factored that out, couldn't I? I'll show you what I mean, right? Like, we could say, okay, if we're doing the interval from 1 to 11 using 5 rectangles, we know that delta x is going to equal 11 minus 1 over 5, which is 10 over 5, which equals 2. And I guess we're going to have, the area is going to be f of 1 delta x plus f of 3 delta x plus f of 5 delta x. Whoop. Right, etc., right? Because we're just adding up rectangle areas, right? Whoop. Right? But I guess we really could have just done it this way, right? F of 1 plus f of 3 plus f of 5 plus f of 7 plus f of 9 all times delta x, right? So let's do that. And again, I am not going to simplify this because this is kind of gross, right? Negative 1/2 plus 3 times 1 plus 5 plus, and then f of 3 is going to be negative, so I guess this will be negative 9, right? Let's just be clear where I'm getting this. It's negative 1, so it's negative 3 squared over 2 plus 3 times 3 plus 5, negative 5 squared over 2 plus 3 times 5 plus 5, and we just keep doing this, right? Negative 7 squared over 2 plus 3 times 7 plus 5, negative 9 squared over 2, right? We just sort of keep. And then just make sure, do not forget to multiply by your delta x, right? Okay, don't forget to do that, okay? That's the formula with left-hand endpoints. Now with right-hand endpoints, it's going to be almost the same thing. In fact, I'm going to copy this. Because it's pretty similar. The only difference is that instead of this first term, I'm going to replace that with the last term, right? And, of course, really what I'm going to do is I'm going to do f of 3 plus blah, 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 blah. You get it. Plus f of 11. Delta x. Okay? And so that's going to be, again, just going to abuse the copy paste here. All right. All right, so we'll say that this equals that plus that plus that plus that, and we're not going to do the times 2 yet, because I guess we have the minus 11 squared over 2 plus 3 times 11 plus 5, and all of that gets multiplied by, well, all of that gets multiplied by 2. Okay, so that's our answers. Our answer's similar, I'll say no, because this is a big term that does not appear in the other one. Do we think either is close to the correct answer? It turns out the answer is no, and we'll worry about that next time. But for right now, that's how you approximate.